I am TLP. Now I explain Module 2 of Engineering Physics, that is Elastic Properties of Materials. As I explained in the last class, there are 3 chapters. So in the last class I explained the first chapter, I am continuing that. So chapter 1, Elasticity. Here you are going to study elastic moduli. First one, Young's modulus. The ratio of longitudinal stress to linear strain within the elastic limits is called Young's modulus, and we can write Young's modulus like this: longitudinal stress by linear strain, and write the formula for longitudinal stress as F by A and linear strain as X by L. Then we get FL by AX. So this is the formula for Young's modulus, and by writing unit for all terms in that formula, we get a unit of Young's modulus as Newton per meter square. Second one, bulk modulus K. The ratio of compressive stress to the volume strain within the elastic limits is called bulk modulus. So bulk modulus is equal to, we can write this as compressive stress by volume strain. So apply the formula for compressive stress as F by A, volume strain as V by V, then we get P by V by V, since P is equal to F by A, where P is a pressure, and capital V is a original volume, small letter v is a change in volume, and unit of this bulk modulus is Newton per meter square. Now I'll go for third one, that is rigidity modulus N or eta. The ratio of shearing stress to the shearing strain is called shear modulus or rigidity modulus of the material. So rigidity modulus is equal to tangential stress or shear stress divided by shear strain. Apply or substitute formula for that, F by A divided by X by L, then we get FL by AX. Here also unit is same as that of previous modulus of elasticity, so that is Newton per meter square. So by taking this Young's modulus, rigidity modulus and bulk modulus, we will define two terms. First one, longitudinal stress strain coefficient, and second one, lateral strain coefficient. I'll go for first one, longitudinal strain coefficient. It is represented by alpha. It is given here. The longitudinal strain produced per unit stress is called longitudinal strain coefficient. So longitudinal strain coefficient we can write according to the definition as a longitudinal strain divided by unit stress. So longitudinal strain is X by L and unit stress is taken as a T. So we can write this as X by TL. Second one, lateral deformation. In the case of any deformation taking place along the length of a body due to longitudinal stress, there is always some change in thickness or diameter of the body. This change in thickness or diameter occurs in a direction perpendicular to longitudinal stress, and it is called as a lateral change. So consider a body here which is shown, length of the body as a L and diameter of the body or wire is taken as a capital letter D. Apply force. Longitudinal stress is applied downward. Due to that, there exists a change in length as a X, small letter X, and diameter also changes from capital letter D to small letter d. That means as length increases here, diameter decreases. So now we can define lateral deformation. Change occurs in a direction perpendicular to longitudinal stress is called lateral change. If a longitudinal stress is acting along a wire of cross section, we take that cross section area as A, produces a change in diameter as a D. So lateral strain is defined as it is the ratio of change in diameter or thickness to original diameter or thickness. Suppose if I consider diameter changes here, so I can write lateral strain is equal to D by D. No unit for that. By taking lateral strain, we can define lateral strain coefficient beta. The lateral strain produced per unit stress is called as a lateral strain coefficient. So according to the formula, we can write this as a lateral strain by unit stress. So lateral strain is a d by d, unit stress is a t. So we can write beta is equal to d by t d. So this is a lateral strain coefficient. By taking longitudinal strain coefficient and lateral strain coefficient, we can define Poisson's ratio. So Poisson's ratio is given by sigma. Within the elastic limit, the ratio of lateral strain to the longitudinal strain is a constant, is called Poisson's ratio. So we can write Poisson's ratio is equal to lateral strain divided by longitudinal strain. So lateral strain is d by d, longitudinal strain is x by L. Therefore, we can write Poisson's ratio is equal to LD by XT. So now we have formula for alpha, beta and sigma. Now we'll write the relation between alpha, beta and sigma. So substitute for beta, substitute for alpha, we get beta by alpha is equal to LD by XT, which is equal to sigma, where sigma is called as Poisson's ratio. Therefore, we can write sigma is equal to beta by alpha, where beta is a lateral strain coefficient and alpha is a longitudinal strain coefficient. Now we'll take three relations. First relation between shearing strain, elongation strain and compression strain. Look at this diagram. Consider a cube. This is one cube whose lower surface ds is fixed. This is that lower surface ds, it is fixed to a rigid support, and APSD, AP and SD, B its a front surface. This is the front surface. If a tangential force F is applied, this is tangential force F, it is applied at the upper surface. This is that upper surface AP in a direction shown in the diagram. So it is shown here. The cube will be sheared to the shape A dash P dash SD. This is A dash P dash SD through a small shearing angle theta. So theta is called as a shearing angle. In this way, the diagonal DP will be elongated. So two diagonals are there here, DP, it is shown here, and AS. DP will be elongated to DP dash. So DP dash is shown here. And the diagonal AS will be compressed to A dash S. So AS is this diagonal compressed to A dash S. It is shown here. This is that A dash S. If PX is drawn, I will rub that changes. If Px is drawn perpendicular to P dash D, say this is that Px, it is drawn perpendicular to P dash D. P dash D is shown here. And A dash Y to AS. A dash Y, this is that, it is drawn perpendicular to AS. Then dP is nearly equal to dx. dP is nearly equal to dx. This A dash S is this, is nearly equal to ys. It is given here ys. Ys is this distance. Now P dash x is this, is the extension in an original length PD. So this is original length is a PD. So extension in PD after applying a force is P dash X. So this is P dash X. It is extension. And AY is the contraction. AY is this. It is the contraction in an original length AS. So original length is this is. Due to applying force, there exists a contraction in AS and extension in DP. So now we'll write elongation strain along PD. So elongation strain along PD is equal to increase in length divided by original length. So increase in length is P dash X. Original length is PD. This is original length. So we can write that as P dash X divided by PD. It is shown in the next slide. P dash X divided by PD. Similarly, compression strain along AS is equal to AY divided by AS. Change in length divided by original length is AS. It is given here. Taken that as equation number 1 and 2. Length of each side of the cube is given as L. Then by applying Pythagoras theorem, we can write AS is equal to PD, that is equal to root 2L. Since AD square, this is AD square plus DS square is equal to AS square. AS square. So by simplifying that, we get AS is equal to PD, that is equal to after taking square root, we get root 2L. Now we'll take cosine of angle P dash. Cos of P dash X. See, this is that P dash X. Cosine of the angle is equal to adjacent divided by hypotenuse. So adjacent is here P dash X and hypotenuse is P dash. Therefore, we can write cos of P dash X is equal to P dash X divided by P dash, or P dash X is equal to P dash cos of P dash X. So that is equal to P dash cos A P dash D. A P dash D. Because they are nearly equal, we can write like that. Continue with that. Here APD, angle APD is this, APD, that is equal to 45 degree. But theta is very small, shearing angle is very small. So we can write angle APD is equal to A dash P dash D. Reverse it is written, that is equal to 45 degree. So in the last equation, here it is given, this is that equation, we will substitute for angle AP cos of APD as 45 degree. Here it is given. So cos 45 degree is 1 by root 2. So we can write P dash X is equal to P dash divided by root 2. Substitute this in equation 3 and 4. Substituting these two equations 3 and 4, P dash X as well as equation 3 is this PD. Substitute this in equation 1. This is that equation 1. We get elongation strain is equal to P dash divided by 2L. Here P dash divided by L is taken as a shearing angle. It is shown here. Shearing angle theta is equal to P dash divided by L. Substitute that here. We get elongation strain is equal to theta by 2. This is elongation strain. In the same way, we can calculate compression strain observed along AS. This is compression strain. Here elongation strain what we have calculated. We get a same answer as a theta by 2. Now we'll add compression strain as well as elongation strain. So elongation strain plus compression strain, that is equal to theta by 2 plus theta by 2. So we can write this as a theta. So theta is a shearing strain. So we can conclude like this: elongation strain plus compression strain is equal to shearing strain. This is about one derivation. We'll go for another derivation. Relation between y, n and sigma. Y is Young's modulus, n is a rigidity modulus, and sigma is a Poisson's ratio. Diagram is the same. Slight changes I have done here. Instead of force, I have taken stress. Here we have taken shearing stress as a T. Then remaining part of the diagram is same. So consider a cube of length L. Length of the cube is L under the action of tangential stress T. Tangential stress is T along AP. AP is this direction, along AP, like this. The cube gets sheared to A dash P dash SD. A dash P dash S D after applying stress. The diagonal AS undergoes contraction. AS undergoes contraction and diagonal DP undergoes elongation, like this. The shearing strain along AP is equivalent to longitudinal strain along the diagonal DP. This shearing strain is equal to longitudinal strain along DP. So we get longitudinal strain here, and lateral strain along diagonal AS. Here we get a lateral strain. We studied in the last derivation also. This lateral strain is perpendicular to the diagonal DP. So this lateral strain which occurs here, it is perpendicular to the diagonal DP. These longitudinal strain and lateral strain together produce extension along DP. Okay, we have to consider longitudinal strain here and lateral strain here. Both produce extension along DP. But total extension along DP is equal to P dash X. So P dash X is the total extension along DP. So we can write this P dash X as equal to dpt. Dp is original length, T is applied stress, and in terms of alpha and beta, alpha is a longitudinal strain coefficient, beta is a lateral strain coefficient. So again P dash X is equal to root 2 LT alpha plus beta. Here dP is equal to root 2L. In the last derivation we have taken dP is root 2L. By taking Pythagoras formula we get this. From equation 4, in the last derivation, just to check out once, equation 4, we'll apply that equation, same equation again here. P dash X is equal to PP dash divided by root 2, that is equal to X by root 2, because P dash is equal to X. Next, we'll write P dash X as X by root 2 and P dash X as this equation. Compare these two equations, and we'll write this as root 2L T alpha plus beta is equal to X by root 2. Here take this root 2, do cross multiplication like this, and it becomes 2 of alpha plus beta. Take that L in T to right hand side, it comes to denominator, that is equal to X by TL. Once again invert that this equation. Inverting that equation, we get 1 by 2 1 multiplied by 1 by alpha plus beta. Here also TL by x. So here you rewrite this T by TL by x as a T by x by L. X by L is a shearing strain. So that is equal to T by theta. So tangential stress or shearing stress divided by shearing strain gives what? Rigidity modulus N. So we can write that as N is equal to this. N is equal to N is equal to this. It is written here. Again take alpha outside the bracket. So 1 by 2 alpha, 1 plus beta by alpha. But beta by alpha is Poisson's ratio, sigma, substitute that here. So we get N is equal to 1 by alpha. Alpha is taken to the numerator, 1 by alpha. Here 2 into 1 plus sigma in the denominator. Okay, now we'll go for next simplification steps. Now I'll take the definition of Young's modulus. It is the ratio of longitudinal stress to linear strain or longitudinal strain. It is given here. So we'll rewrite that as 1 by longitudinal strain by stress. So this is general formula and we will apply for this case. So Young's modulus Y is equal to 1 by longitudinal strain. So longitudinal strain occurs along dP. So we can write strain along dP divided by unit stress. So strain along certain direction divided by unit stress is taken as alpha, that is longitudinal strain coefficient. So this is longitudinal strain coefficient. So we can take equation 7 again. This is that equation 7 N, and we'll substitute for equation 7, that is N is equal to, instead of 1 by alpha in equation 7 we write that as Y, Young's modulus, divided by 2 of 1 plus sigma. So rewrite this equation, we get Y is equal to 2n of 1 plus sigma, which is the relation between, this is the relation between Y, n and sigma. We'll go for next relation between K, Y and sigma. That is a bulk modulus, Young's modulus and Poisson's ratio. So consider a cube of unit length, breadth and height. So unit length, breadth and height. Let Tx, Ty and Tz, Tx, Ty and Tz be the outward stresses acting along X, Y and Z directions. Okay, 3 stresses are given here. Let alpha be the elongation or elongation strain coefficient along the direction of forces. Beta is considered as lateral strain coefficient. Then a stress like Tx, okay, where is Tx? Tx here produces an increase in length of alpha Tx. So increase in length of alpha Tx, and stresses Ty and Tz produce a contraction. So it is written in terms of beta, beta Ty and beta Tz respectively in a cube along Z direction. Sorry, in the cube along X direction. I am talking about X direction now. So we will take derivation. Length of the cube along X direction. This is X direction. Before applying stress is 1. Length of the cube along X direction after applying stress is given by 1 plus alpha Tx minus beta Ty minus beta Tz. Similarly, along Y and Z directions, the respective length becomes 1 plus alpha Ty minus beta Tz minus beta Tx. and along z direction 1 plus alpha tz minus beta t x minus beta t y. So we have length along x, y and z. So volume of the cube is taken as meter cube, length into length into length. So we'll multiply that. 3 lines along x, y and z. Here alpha and beta are very small. Longitudinal strain coefficient and lateral strain coefficient are very small. The terms which contain either powers of alpha and beta, that means alpha square or beta square or alpha beta, they are neglected. Simplification step is not written here. By neglecting alpha square, by neglecting beta square, by neglecting alpha beta, we get new volume of the cube as equal to 1 plus alpha tx plus ty plus tz minus 2 beta tx plus ty plus tz. So again rearrange that. 1 plus alpha minus 2 beta. Here tx plus ty plus tz is common, taken that outside. Remaining is alpha and minus 2 beta, so alpha minus 2 beta. Here length of the cube, it is a cube, so length of the cube is taken as 1 before applying stress. Okay, and stress also same, tx, ty, tz is equal to t. Then the new volume is equal to, substitute this, which one, tx is equal to ty is equal to tz is equal to t, substitute this here, we get a new volume is equal to 1 plus, plus is added here, of alpha minus 2 beta into 3t. Since the cube under consideration is of unit volume, increase in volume is equal to 1 plus 3t alpha minus 2 beta minus 1. That is equal to 3t of alpha minus 2 beta. So we get a increase in volume like this, 3t minus alpha minus 2 beta. So instead of outward stress T, a pressure P is applied. The decrease in volume is equal to, same equation what we have written earlier, same thing we'll write here. Instead of T, we'll write that as P. Pressure P of alpha minus 2 beta. So volume strain is equal to change in volume divided by original volume. Change in volume is this, we'll write here. Original volume is 1 because the length of a cube or edge of the cube is unit. So bulk modulus formula you write, K is equal to pressure by volume strain. So that is equal to P divided by 3P of alpha minus 2 beta. This one is written here. Cancel this P. Cancel this. We get bulk modulus is equal to 1 by 3 of alpha minus 2 beta. Again take alpha outside. We can write 1 by 3 alpha of 1 minus 2 beta by alpha, but beta by alpha is a sigma Poisson's ratio, and take that alpha to the numerator. We can write that as 1 by alpha, but 1 by alpha is taken as a Young's modulus. In the previous derivation we have taken like that. So K is equal to y divided by 3 of 1 minus 2 sigma. So this is the relation between K, y and sigma. Bulk modulus, Young's modulus and Poisson's ratio. Or we can write this equation as y is equal to 3k of 1 minus sigma. You can cross multiply this. So limiting values of sigma. So just now we have derived 3 equations. Out of that 2 equations we'll take y is equal to 2n of 1 plus sigma, y is equal to 3k of 1 minus 2 sigma. In the left hand side of the equation is y. So by equating that we get 2n of 1 plus sigma is equal to 3k of 1 minus 2 sigma. If sigma is given any positive value, left hand side is anyhow it is positive. If positive value is given here, left hand side becomes positive. But right hand side, to get positive value, sigma value should be less than 0.5. Suppose if I substitute sigma as 1, I get a negative value on the right hand side. So to avoid a negative value on the right hand side, you have to substitute sigma value as less than 0.5. Next, suppose second case, sigma is given negative value. So right hand side is anyhow negative. If you substitute sigma for as a negative value -1, -2, etc., you will get a positive value here. But suppose if you get a substitute negative value here, you get either 0 or negative value. But whole answer should be positive. So left hand side should be substituted as a sigma is greater than -1. So two values for sigma we can apply. Sigma is less than 0.5, sigma is greater than -1. But sigma is greater than -1, that means negative value for sigma means elongation and lateral expansion takes place in a material, but it is not possible. When elongation takes place, there exists lateral contraction.